Okay, so this question looks like a Fat March 2-3 question. Am I right? Hang on, let me dig a bit. And while just want to give you some context if you have not seen this question yet. I'm sending the question into chat, but this is from Fat March 2-3. So the question was, what is the cause of the induced EMF? Because we all know that in order to have induced EMF, there needs to be a change in flux. Okay, so right now, this question is a lot of words but no story. So I tell you the story lah, or maybe I draw something for you. Okay, so part A has nothing to do with part C. It's just how to use a Hall probe. So in case you don't know or you don't really understand the use of a Hall probe, the Hall probe is mainly used to measure magnetic field. So if you look at part A, it says here that if you place it in a magnetic field, the Hall voltage is 0. And then sometimes in a new position, the Hall voltage is maximum. It really depends on how the Hall voltage interfere with the magnetic field. So it's worth remembering that the magnets that we are working with are most of the time electromagnets. So if it's electromagnets, let's say you have a cylinder here, okay, and there be some coils, all right? I draw the cylinder there to make the coil a bit more obvious, but this is the coil, okay? So it's going to coil all the way. And so dot, 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 and then you'll come back here. Inside, you will have a magnetic field this way. Okay, so in the middle, we've already understood that the field here is uniform. So from now on, whatever I draw inside here is basically the magnetic field. Obviously, the direction of B will depend on the direction of my current. So since I already draw B like that, current is going to go in this way. All right. So if let's say there is a gap here, okay, most of the time when we coil this kind of coil, we will use the Helmholtz coil method. So let me show you how that looks like so that I don't have to draw. A Helmholtz coil from my notes will look something like this lah. Okay, so it looks something like this. Right? You have two coils and a coil it in such a way where it connects to the other coil. Okay, so what this one does is, based on how it's being set up, your current, I'm going to use blue for current, your current is going to flow this way and then go to the back and then come to the front. Okay, not. And then go to the back and then come to the front. And then the back and then come to the front. So that's why you have the magnetic field. If you use your if you use your right hand grip rule, you will grip your finger pointing downwards. Your thumb will be pointing towards the direction of B here. But notice that in the middle here, there is uniform magnetic field. And I can measure this uniform magnetic field B by placing a Hall probe inside. Okay, so if let's say this is my B, and if I place my Hall probe slice in such a way where the magnetic field enter perpendicular to the Hall probe, so visualize the Hall probe as something that we've learned before, which is this. So the Hall probe looks like this. Okay, but if I zoom in and look at the slice looks like this. Okay or not? So this slice, this one here, maybe I'll rotate it. Nah, okay. So this is a magnetic field and this is the slice. This slice exists here. I zoom in and look at a piece of slice, but it's actually a probe. Okay? Does that make sense? So we use the Hall probe to measure magnetic field. So when you put your Hall probe this way, when the magnetic field and the slice is perpendicular, then you can use the equation VH is BI over NQT to calculate B. That is, if you know the current going into the slice, so most of the time this is the current I. If in the Hall probe, then this is the current I. Okay, N would be the number density, which depends on the type of material. So if you check out the question, let me pull down a bit so you can see. If you check out the question, different material will have different N. Okay, T would be the thickness. So based on all my drawings here, the thickness must be parallel to B. So this is my T. Of course, inside here, you can't really see what the T is. So it's somewhere here. And then Q would be the electronic charge. But most of the time, when we use the Hall probe, we will calibrate it using a known field. So what does calibrate using a known field mean? Well, it means that I don't have time to use this equation all the time. It's not suitable for my experiment. So what I'll do is, I will then, number one, okay, let me write down. Purpose of Hall probe to measure and detect magnetic flux density. B. Okay, it's not, it's just really just one purpose. And when using Hall probe, number one, or rather step one or point one or additional detail, you will calibrate using a known field. So let's say, for example, before I even use my Hall probe inside the solenoid on top, inside the coil on top, I use it here first. Because maybe I know this magnet. Maybe this is a familiar magnet. Maybe I know this magnet bar is a very solid, very well-made magnet bar. And this magnet bar has a magnetic flux density of, I don't know, 24 millitesla. Example lah, okay? And then when this one has a magnetic flux density of 24, wait, let me check. Okay, sorry, not 24, 32 millitesla. This one is already known to the experimenter or known to us. So another example of calibration using something that you already know is like you calibrate a thermometer using a known boiling point. So if you take a thermometer and then you want to draw the scale, how do you know how long is 100 degrees Celsius? You stick it inside boiling water. This is 100. So this one will be inside boiling water. And then after that, what do? You stick it inside melting ice. And then your thermometer maybe have this length. And then you will stick this one as 0 degrees Celsius. Now, what happens between 100 and 0? You draw a bunch of intervals and you make your thermometer. I just described the process of calibrate thermometer using known fixed points. Boiling point. Boiling point is boiling point and melting point. So the Hall probe is the same thing. In fact, all physics experiment is the same thing one. It's either the calibration is done for you like a ruler, someone already marked for you and you just use only, or you don't know what is the new calibration of the day. Maybe the equipment is slightly different today due to environmental factors and you need to calibrate it again. Then calibrate again, no? Okay. So let's say I have a fixed magnet for calibration, okay? And this is known to us, just like the boiling point and melting point is known to us. Then I stick a Hall probe here and I run the Hall probe through the magnetic field. So maybe now my Hall probe is here. Okay. And this is my slice. Maybe I'll zoom in a bit. So I purposely want a scale drawing for you to understand that in real life, we can't really tell what the slice is now. But let's say this is my slice that is inside, and then inside here is part of the whole probe wall, so the slice is here. Okay, the slice is here lah. All right. So when the slice is inside and the magnetic field cuts through it this way at a 90-degree angle, this Hall probe, which is also not just current come in, is also connected to a voltmeter. This voltmeter tells me that the Hall voltage is 24 millivolt, or the voltmeter will be connected here, 24 millivolt. So when you are zooming out at this scale, we don't really bother to show that, okay, I'm connecting the Hall probe with the current in this phase and then the voltmeter across these two other phases. It's not really that important because we're talking about this scale, but it's of course important if I zoom in. By the way, the focus of the experiment is not the zoom in diagram, it is this one. So if I know this, I know when VH is 24, B is 32 millivolt. This means when I calibrate using a known field, I can draw a graph of VH against B. And based on this equation, VH is BI over NQT. For the same device, VH is proportional to B. So you're going to get a straight line. How do I know how to draw a straight line? Very easy only. I just find 32 millitesla and 24 millivolt. I draw a cross here and this is my calibration curve or calibration line. Okay. And then now I take the same Hall probe and I stick it inside here. If I take the same Hall probe and stick it inside here, and I don't rotate the Hall probe, we'll talk about the rotation shortly, and I don't do anything to the Hall probe. And this Hall probe, the voltmeter reading is 24. No, no, no. Okay, let's say it is 30, based on the question lah. 2, 4, 6, 8, 10. Let's say it's 36 millivolt. So how do you find what is the value of B here? Well, you go and find 36 on your graph law, then you dot, 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 dot. This will be your B of your coil. This is the magnetic field of the bar. Bar would be this one. All right. So the first thing you need to know about the Hall probe is we exploit this relationship a lot. VH is proportional to magnetic field, which means whatever happened to B happens to the magnetic field. If I double the magnetic field, I will double the VH. If I half the magnetic field, I will half the VH because they are proportional. Okay? All right. Second thing, just based on this 90-degree, how do I know that the magnetic field is 90-degree to the silicon inside? I cannot zoom in also. I also don't know how to install the silicon. Correct, you don't know. That's why you rotate until you get 90-degree. Okay, so this sort of answers this part of the question. If let's say this is your slice, let me try to draw in a way where it's easier for my hand. Let's say this is your slice. Then your magnetic field is this way. In this case, VH is maximum. But then when you are like this, and the magnetic field pass through like this, then your VH is 0 because it doesn't cut through 90 degrees. Okay, your current is still going to enter the same phase, so this will still be your I. and your hall voltage is still going to be, because we don't change the connection of our circuit in our probes, what? You're not going to screwdriver open the probe casing and adjust it. It's basically just a device that you adjust. So your VH is now here and here. Okay. So if I rotate it in such a way where the magnetic field doesn't pass through the slice, at least through the phase that I expect it to, based on the connection that I've already wired the Hall probe, my reading will be 0. Okay. So if you're doing paper 5, for the additional detail, you want to say calibrate it using a known field. And then another additional detail is you will rotate the probe until VH is maximum. And then what do? You clamp. You don't clamp, then you hold, you expect your hand to maintain the same angle. Not possible. Okay. So you will put the Hall probe inside this highlighted yellow position, and you slowly turn until your VH is maximum. And then you take a clamp and you clamp the Hall probe in place. Like a selfie stick. Physicists have been using selfie stick and tripod even before social media. Okay, we kept it lah. Scientists have been using clamps many time, many years, I mean. All right. So these are additional details that you may want to write for paper 5, but it's also useful to think about when you see a question like this. Okay. So this part, you can check out the mark scheme about how they explain, but basically they just describe my drawing. It's perpendicular to the plane of the slice, the VH is maximum. Once it is rotated such that it is parallel to the plane of the slice, VH will be 0. All right. So in this case, I'm just going to assume that they put it in a fixed position, and I have used this as an example just now for my calibration. So this entire sentence implies calibration, or calibrate using a known field. So this means if I again draw a graph of VH against B, there will be a point where this is 32 millitesla and this is 24 millivolt. And then it says that the same Hall probe is then placed with a magnetic field of fixed direction and varying flux density. So if the direction of magnetic field change, the VH will be negative. So because the direction is fixed, VH in this case is always positive. Anyway, it is also in a fixed position so that the angle between the Hall probe and the magnetic field is the same when the Hall voltage is 24 millivolt. So it's already clamped in place and we no longer want it to move. Clamped, ED. Okay, so let's interpret the graph a bit. If the VH against T graph looks like this, can I say that my BT graph will also have the same shape? Because why? VH is proportional to P. Okay. So from 0 to this time, which is 3.242, 3.2, 3.2 second. Look, this one here is 36 one. So if I just use a simple ratio, let me press my calculator. I use simple ratio. 36 millivolt. So 36 over 24 millivolt is equal to 32 millitesla over B. So 36 over 24 times 32. So B will be 48 millitesla. So this one is 48 millitesla, time in second. It will stay at 48 until this point here, which looks like 7.2, and it will eventually drop to 0 at 8.6. So we can calculate the maximum EMF by looking at the maximum gradient, which is here. Because if you want to find EMF, I mean, they gave us N and they gave us the diameter of the coil. So what happens now is step 1, I have this electromagnet. Let me find it. Hang on. So I don't want to draw again. Don't want to draw again. Okay, so step 1. At this position, they put a Hall probe here. Let me zoom out a bit and arrange my screen a bit so you can see. Okay, so step 1, they take the Hall probe, they put here, Hall probe, and then they get the VH graph. Okay, based on our understanding of VH, we get the magnetic flux density graph. So I know the magnetic flux density will change this way. Inside the coil, this P. Okay, and then the next part is a coil, the second part, I have another coil. It is not this coil. This is another coil, a coil of 780 turns, and this diameter is placed in this varying magnetic field. Remember, this was your varying magnetic field. How do I know? Well, how do they vary the magnetic field? They change the current? Maybe I put a rheostat here or a variable resistor here. So vary I to vary B. So there are a few things here to think about. I change the current in the coil, this I, and the B will change because I is proportional to B. 1. Number 2, they don't even tell you how they vary. So the focus of the question is not really this, but if you are asking why is there a change in magnetic flux, because I changed the current. I changed the current, I changed the magnetic flux density B. How do I know? So this first part is how to change B. The second part is how to measure the change in B. Let's say you don't have information about the current or you don't know how the current is changing. Then you will use the Hall probe. Because similarly, VH is proportional to B. Okay? I change the current, I change the field. In order to measure that changing field, I stick a Hall probe inside. Now I already know how the current will change and how the field will change. The next step would be to take a coil. So there's a coil here. And I will put it inside here. And connect to another voltmeter to measure the induced EMF. So this one is induced EMF. But this one, this Hall probe, although it is still a voltmeter, this voltmeter is to measure Hall voltage. Okay, so I repeat, because somehow this part a bit hard to brain. Maybe the setting, to be fair to you, it's not like anybody get to do this in the high school lab also, so it do be like that. I have a coil. If I change the current in this coil, I will change the magnetic field. When I change the magnetic field, I don't know the magnetic field is changing. Let's say I want to see and measure the magnetic field change. Then I will stick a Hall probe there to measure the change in field. Okay. Then finally, number 3, you want to calculate the induced EMF. Induced EMF is not just the change in B. It's the change in flux over the change in time. Okay. So that's why when you reach here, you want to find the EMF that is maximum. You will take the change in flux over change in time, but the flux is NBA. And I know for a fact that N and A doesn't change because the only thing that change is B. And you want the maximum dB dt. So you will do your calculation. Does that make sense? So in short, because VH change, so because VH change, that's how I know the magnetic field or B changes, magnetic flux density changes in the exact same way. Because I know the magnetic flux density B changes in the exact same way, I will also know that the magnetic flux changes in the exact same way. The numbers will be different, right? Like this one was 36 millivolt there, but then it is 48 millitesla. And if I care to, I can calculate this. In fact, I'll probably be calculating it anyway. Flux against T. So this one will be a different number because this will be NBA. But all this graph is the same because from here to here, B proportional to VH. From here to here, flux proportional to B, which makes flux proportional to VH also. And finally, you get the thing that you want, which is the induced EMF, T, E against T. But obviously, they are not proportional because it is the rate of change. So here you will draw the gradient function. Okay, induced EMF, if you want to include Lenz's law, is negative the flux dt. So it is negative the gradient of the flux T graph. But it's also the shape of the gradient of BT and the shape of the gradient of VT, VHT. So let's say the magnetic flux increase, I don't want it to increase, so I will decrease in the opposite direction here. Okay. And then when the magnetic flux doesn't change, and how I know the magnetic flux doesn't change? Because the magnetic field did not change. How do I know the magnetic field didn't change? Because the Hall voltage didn't change. So here will be 0, no? And this will be double. Not double, it will be bigger. I don't know, need to calculate. Okay, so this is the actual EMF, the induced EMF. So to answer your question, because I feel like if you're asking a question, maybe there could be a misunderstanding. What causes the change in magnetic flux density is the fact that the current in this coil is changing. So they didn't even tell you what is this magnetic flux density from. So you just got to accept that there is a magnetic flux density that is fixed direction. There's a magnetic field in a fixed direction and varying flux density. Why is there a magnetic field? I can provide a conjecture lah. Perhaps there is a setup like this where I can change the current to change the magnetic field. How do I know there is a change in magnetic field if I don't know that the current is changing? Well, I have information about the changes in Hall voltage, which I can then deduce the change in magnetic flux density, B, and then deduce the change in magnetic flux linkage or magnetic flux, phi, and then deduce the induced EMF. Okay, so in short, the cause of the change in magnetic flux is a changing current in the coil. Likely, but it is not entirely certain because the question didn't tell me. The question just say that the B is changing, but they didn't specify what caused the change in B. Without that context, I can give you some guesses. The current can change. Other things could be maybe they move the coil, but that is a bit weird lah. So most of the time it's the current changing lah. All right. Let me know if there's any follow-up questions. We continue. Let me find more questions about magnetic flux. Is the current alternate? Which current? Current in the coil or induced current in the orange coil? Which, the black color coil or the orange coil? The black one. The black one, the current is not AC because VH didn't change polarity. Magnetic field is a fixed direction, implying that the current is a fixed direction. But the orange coil, the induced EMF, I guess you can call it an AC because it has both positive and negative direction. Okay. The next question comes from also induced magnetic field or the induced EMF. This one is from Winter. Let me write down the year number for you. I'm going to send images to the chat if you need it. But this one is ON22P41. We've already discussed this in class 1. There's just a follow-up question of why is there a magnetic field in Q? Okay, so like this, again, we go one by one. So right now, this question, the starting position is at first the switch is placed connected to the battery. Okay, and the battery will charge the capacitor. So this will be positive, 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 negative, 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 until the potential difference is 24 volt, in which the charging will stop. Capacitor is considered fully charged, at least to the capability of this power supply. Okay, and then we will move the position, the switch S to position Y, so that the capacitor discharges through wire P. Okay, so when the capacitor discharges through wire P, this means that the switch is now here. This one no more already. And then suddenly the electron be like, hey, I have missed you, positive plate. I am going to neutralize you. I am coming. So the negative charge will come down. If the negative charge goes in this direction, it also means that current flows in the opposite direction, conventional current flow. Okay, so first explanation, or rather, maybe the explanation is here. Number one, there is current flow in P. Number two, magnetic field BP is set up. I think this part is okay, right? Because current is flowing and this is a straight conductor, you can use the right-hand grip rule. The current, the magnetic field is like that. It's a turn lah, but if I want to draw a 2D version, it's going like that. Here is in, then here is out. But here is also out. And here is also out. Because the field extend far, far away. What? Make sense? So then let's talk about Q. Step 3. Q is inside the field of P because they are close enough to each other. I mean, of course, it extends to infinity, but they're close enough to each other. Meaning whatever changes that P goes through, Q will experience a same change. This is basically two parallel wires, but it's basically Q is inside the field of B. So as the capacitor discharges, wait, let me move here a bit. We already draw the graph. Just do a sketch here. The IT graph will look like this. At first, the current will flow very fast, or rather, we have a large value because a lot of charge will flow. Eventually, as the capacitor empty, the charge flow will drop. Yes, no? I is I naught E negative T over RC. Okay, so as capacitor discharges, BP, or rather, I changes as per this graph, and BP is proportional to I in P. This is I in P. So BP will also have the same graph. For the same reasons as the previous whole group question. Why I want to draw again? I just copy paste the graph. So this one is the magnetic field. Again, the values of the y-axis will be different, but the shape of the graph is going to be the same because B is proportional to the current. BP is proportional to current in P. What about flux? Because Q is inside the field of P, which also implies as BP changes, Q also experiences a change in flux because the flux of Q is equal to BP times the area. If you ask me what area, it is actually the surface area. But there are many, many layers of surface area. You imagine like a Swiss roll, but circle, like many, many cylinders wrap around each other. Layer by layer, there will be area, another layer, another area, another layer, another area. In other words, we do not have the calculus to think about the change in area together with the change in magnetic field. Two things are changing. We don't want to think about it lah. No, got change can already. Okay. So the induced EMF will still follow the same pattern, but there will be no calculation here because this, if you want to write down the equation is your syllabus, your maths is here lah, right? Where my nose is. But the maths that you need to do the mathing is uni maths. You need university level calculus to do that. All right. But we can at least start the process now by visualizing what is going to happen. So if BP changes like this, and because this one is this, I can still somewhat reasonably say that at a point on the wire, if the area is kept constant, so basically I don't integrate outside of the wire, I basically just choose a point on the wire and just fix myself on that point, which is a fair assumption to make because you are connecting the voltmeter across the wire. So maybe I just take the surface of the wire. Okay. So then the flux in Q is proportional to BP, which brings me to the point where I can paste the graph again and call this the flux in Q. And based on my understanding of induced EMF, the induced EMF E is proportional to the rate of change of flux in Q over dt. EMF in Q, Faraday's law. But you see, if I differentiate the exponent graph, won't I get another exponent graph? D dt e to the power of negative t over RC. And then got some constants in front. Wouldn't I get negative 1 over RC d dt e negative t over RC? So the beautiful thing about exponents is You differentiate an exponent, you get back the same exponent. Just again, the y-axis changes. So from here to here, you d dt exponent, you get back the same exponent. But teacher, I don't do maths. I have no idea what you're talking about. Okay, no need to do maths. You can just check out this one. This is the induced EMF in Q, EQ. If you understand maths, the graph makes sense. If you're not, then you think about this one as equal to the gradient of the flux Q against T graph. You see this gradient here, many steep. So here is large value. Lor. You see the gradient here, less steep. So here is small value. Lor. So the gradient is decreasing. So the value is decreasing, but not a straight line. Never a straight line unless you are sure it's a quadratic function. Does it even look quadratic to you? No. So never a straight line. Okay. All right. So the question is, how do I know there's magnetic field around Q? Well, then we continue the story. So again, the story started with IP changes, BP will change, BP proportional to IP, but the flux in Q changes as well because flux Q is proportional to BP. And because flux Q changes, so this is number 3, there is a change in flux Q. Number 4, due to this, there is an induced EMF in Q. Does that make sense? There's an induced EMF in Q. Okay, so right now, we're going to pause here and ask ourselves, does an EMF always imply that there is current? Does EMF mean got current? So I repeat the question. Huh? Does the presence of EMF imply or tell us that there is a current flow? If I have a battery, a very simple 1.5 volt battery, it has EMF, right? Got EMF, right? Got current or not? Oh, this one obviously not. Okay, never mind. I copy. Okay, hang on. Maybe I copy it. I copy this because I know there is EMF across the wire Q. So instead of wire Q, I go and put a battery here, 1.5 volt. Okay, and then I have this voltmeter across the battery. The voltmeter is across this one. So the voltmeter will measure 1.5 volt. But is there current flowing in my mini circuit? No, because the potential difference across I won't say there's no potential difference, but the terminal potential is 1.5 volt. Got EMF doesn't necessarily imply current flow. So it's no lah. So it depends on, is there a closed loop for current to flow? You could, of course, say, isn't Q and voltmeter a closed loop? Just like isn't the battery and the voltmeter a closed loop? It is, but current still cannot flow because the voltmeter does not allow current to flow. The resistance of the voltmeter is very large. This is from AS law. So no current. I can still measure the 1.5 volt, but there will be no current flow. Yeah, you're right. So it's like a battery. There's no potential difference across Q. But then sometimes I can just say that this induced EMF is the potential difference across Q because this is strictly speaking not a battery. So this induced EMF across wire Q is not a potential difference because it is basically some other, so it's the electrical energy of P converted to the electrical energy of Q. So I cannot use the definition of EMF anymore because I'm like, Don't know. Q does not have a magnetic field unless I replace V with a resistor. So I can basically set the same question. I ask you with the voltmeter first, and then I replace this voltmeter with a resistor. If I have in place a resistor here, then there will be magnetic field around Q to interact with P. But in this current state, there will be no magnetic field. Just an induced EMF. So if current is allowed to flow, we can continue the story. Does that make sense? Currently there is no, so this is where the story stops. Because the voltmeter connected to Q stops current from flowing. So the voltmeter stops current from flowing in Q. But if current is allowed to flow in Q, then we would have the current in Q having the same shape and the magnetic field in Q also having the same shape. Then this BQ and this BP will now start to have a conversation, and the force will be repelling one. There is field. The induced EMF, okay, we go back to the step by step again. The induced EMF EQ is due to BP, not BQ. The origin story of the induced EMF in the wire Q is due to the magnetic field in wire P, not the magnetic field in wire Q. So the induced EMF has nothing to do with the wire Q at all. There's no it has nothing to do with the magnetic field, whether there is magnetic field in wire Q at all. So your question of whether wire Q has a magnetic field depends on whether the induced EMF in Q is allowed to push the current in the loop of Q. If yes, if let's say this was my P and my current direction what's the direction of my current again? Down. This is the direction of the current in P. Then this one, this is Q. I want to oppose the change causing it. So I will try to push away. Push away would be opposite direction. This will be your IQ. But no current. So when you look at this flux change, right, every question is a bit different. You have to figure out whether it's your own flux change or your neighbor flux change. All right. So currently Q isn't at a point where it can create its own magnetic field, ergo it doesn't have any magnetic flux. But if it has, then we want to continue the story. So I guess if you want to know, then this IQ the magnitude will be like this, but it will swap direction one to oppose the change. But this two will be opposite. Opposite to IP, and this one will be opposite to BP to oppose the change. In short, you can try out your hand again and do the thing, but I can bypass all of that by thinking of opposition. Okay. The next induction question, many induction questions. Let me try to understand STEM. Okay, if you want to use Fleming's left-hand rule for this one, it's a bit tricky So I will direct you to watch a recording, but I will roughly explain to you first. You should watch the recording from when you dig out the old past year question, May June 21 P42, because it is the same situation as this one. If you want to use your Fleming's left-hand rule, you have to consider, I mean, I'll take a screenshot of this and put it there. But you will have to consider this highlighted yellow color point, because the magnetic field around the coil is actually a circle. So when we take the direction of B, we are taking the direction of B right here where I'm crossing, which is the yellow color highlight. So because on top it will turn in such a way where the magnetic field is actually horizontal. Then you can use your left hand. So likewise, yeah, screenshot and throw there. This one is May June 21 P42. You can search from the channel, because the one will you can slowly use your hand and brain the direction. So similarly, for this question, if you want to think about the using your left hand, you have to actually use this point. And to be honest, I don't want to use the finger lah. I just use my lens. The ring doesn't like that the flux is changing, so the ring will try to get away. I know it will jump upwards. So then I just use forces to deduce, or rather use magnetic field to explain the presence of forces to cause it to jump away. But if you want to use left hand, here is how you have to orientate your left hand, and it has to be at the corner, at the top part. So we do not follow this direction of the blue color field already. We are curving the blue color field in 360 degrees. You cannot use the opposite pole because we need to explain why there is a force for the ring to jump upwards. I understand. I also would like to use the pole to explain, but the mark scheme has never allowed candidates to use the pole, and the same pole or the unlike pole will repel. So I do this thing where I say that I know it will repel. I already know because of Lenz's law. So in order for the repelling to happen, it has to have an upward force. So I deduce in the opposite direction. So normally your brain would want to think like, okay, I want to step by step decide the direction of B, decide the direction of I, use my left hand, decide the direction of force, and then decide whether the ring will go up or go down. That is the direction that your brain wants to go. But currently, it's very hard to use your left hand in this situation. You can try it out using the bottom plane. You can also try out how I use my left hand. So the questions to refer to for this kind of question is May June 21 P42. I think it's question 9. Then there is also a very more recent one regarding the flywheel. I have it here. Yes, the flywheel, which is May June 23 P42 question 6. I think this one is discussed in class, but this one is on the channel. Okay. So they tell you the direction. It's not in class, please. They don't need to tell me. I know it will jump because it opposes the change causing it. So yeah, I know it will jump. I just use the north pole and south pole to convince you further that it is jumping. So if you look at the answer I've typed, first thing I establish where the change in flux is. Second thing, I establish the induced EMF and current. And then now I already have the conditions for magnetic force. Because whenever there's something jumping or moving, there has to be a force, right? Things won't move unless acted on by an external force. This force is a magnetic force. It has to be a magnetic force. There's no other forces that can exist here because there's only a magnetic field and maybe the weight lah, okay? So right now, the magnetic field due to the induced current in the ring or, or interacts with the coil's field. So we got two magnetic field interacting. Or you could say the current flowing in the ring interact with the coil's magnetic field. Initially, you wrote force of the weight is acting downwards to oppose the direction of the force acting upwards. So right now, the change is not weight. The cause of the change is current flowing. Switch is now closed. So this is the cause of the current change. So if you talk about weight, there will be no Marx one because weight didn't cause the change in flux. Current caused the change in flux. It has nothing to do with weight. It's going to jump up. Eventually, the induced current will stop, then it will fall down. The falling down is weight lah. But the question didn't ask you why does it jump up and then fall down. It just say why does it jump up. So you explain that also, no point. Or rather, it doesn't answer the question. Because the starting already, the identifying the cause of the change in flux is erroneous already. It is not weight that causes the change in flux, rather the current flowing that causes the change in flux. So in short, to decide the direction of current or force, I always ask myself, how would I oppose the change that is happening? If I'm unsure whether the opposition looks like the force is, you see this, for this example, the force is actually acting inward or the force is acting outward, like what is going on, I'm unsure of what is going on, then I have to ask myself, I'm the ring, how would I oppose the change? So I use the north and south pole. I use the north and south pole to convince myself the direction of the force here, upward force on the ring. I do not use this one to explain the direction of the force. Okay. Let me know if there is follow-up question for this one. I still don't know whether the force jump up or pull it down. Do you understand this explanation here? The north pole and south pole one? Because currently, when the current flow, the magnetic field of the coil is pointing downward using the right-hand grip rule. The ring will have this downward field. The ring don't like the downward field. It will create the green color upward field to oppose the downward field. When I draw out the field in the ring and the coil, I find that south pole is facing south pole. That's why they jump. That's how I know they jump. And because they jump, so I know there has to be an upward force. And now I have to explain why is there an upward force. So step one, I convince myself it is an upward force. In fact, they already tell you lah, so upward. Then I'll go back and explain the presence of force. Okay. All right. The next question, which is still magnetic fields. Maybe I'll answer a few more so I can get to the class. This one, your question is, how do I know the direction? You don't know. This question is not a very well set question. the mark scheme say Y is like that, but only because they assume that the curvature is this way. So the turning happens here. But how do you know whether it turns here or it turns the way that you have drawn? Don't know. Why not upward leh? I also don't know. So basically this one mark is just a wildcard. There's no way to tell the curvature. I don't have any data points. So don't know. W and Z and X I know. But this point Y, I don't know whether it is at this point of the curvature, which is the mark scheme answer, or the pencil that you have drawn. It could even be vertical upwards. So the possibility should actually extend. They should accept any answer between these two arrows. But never mind lah. Just one mark. Let it go bah. Okay. How do I know whether there is eddy current? Eddy current needs space. So you don't always need to mention eddy. You don't need to mention eddy current. You can just say current. But the short answer to how do I know there is eddy current needs space to build up. So I need a 2D or a 3D conductor. Lagging. Okay. So for example, in this question, your metal block will cut the flux. And when the metal block cut the flux, there will be eddy current inside here. Okay? Because your question is heating effect is due to eddy current. Heating effect is due to current. Full stop. Eddy current is just when there is a 2D space and now your current will flow this way. Spiral. Like a tornado. Spiral. If it's a wire, now the electron cannot spiral. The electron either just move like that or they move like that. No spiral. No eddy. Eddy just means a spiral pattern. But if it's a 2D conductor or it's a 3D conductor, you can spiral lah. Got space to spiral. But you can just don't talk about eddy current, just say current causes heating effect. Current flow through the conductor gets hot. Current flow through the coil. By the way, the coil is also not a spiral, although it looks like it, but the current is forced to move in circles or in a fixed spiral. The eddy spiral is it's not random, but it's a different idea, a different type of spiral. So if you look at eddy, the definition of eddy is a circular movement causing a whirlpool. We are looking at, oh my God, this is a different kind of eddy. Yeah. So the eddy current is always this kind of curvy current, now like that one. Yeah, and like this one, or the curve here. So it is a current that has a larger heating effect and is more applicable only when there is a 2D thing. But then students will get very brain pain now because we can actually tell the direction of the eddy current one, and we can do maths around the eddy current. So if you're just talking about the heating effect, it's fine. You don't have to. But the eddy current is basically the circular current. Okay. Okay, for this one, when the metal passes the magnet, there's a change in magnetic flux in the metal. Okay. It's induced. I'm assuming there's a full stop here. The kinetic energy of oscillation converts to EMF. Kinetic energy doesn't convert to EMF. It converts to electrical energy and eventually to heat. Yes. So it's the same concept that you were asking me in wire P and Q. EMF doesn't imply that there is current flow. So I need a bit more explanation here. The kinetic energy of oscillation converts to electrical energy. Since current is flowing, it will eventually convert to heat. EMF is not energy. So you cannot say energy convert to something that is not energy. Very weird, right? Kinetic energy convert to height as the ball is thrown up. Its kinetic energy converts to height. Cannot low. Cause height. KE convert to height. Height and KE is totally different unit. How to convert? Kinetic energy and EMF totally different units, cannot convert. So you will want to explain that the kinetic energy converts to electrical energy. Since a current is allowed to flow, or current will flow in the metal block because there is no restriction there. There's no voltmeter stopping it. So current flows in the metal block, the energy will convert to heat. So this point here cannot. Okay. It's not an equivalent comparison. So it cannot be converted from one form to the other. The only time you can talk about energy conversion in this way is when you talk about this equation, E is equal to mc square. But why is there electrical energy? Yes, you will lose mark because the energy conversion needs to bring it to the end. You need to follow through. Why does electrical energy causes the KE to decrease? Like where does the energy go? If it converts to heat, it is understandable that heat goes off to the surrounding and is lost. So don't stop at electrical energy. Follow through. In fact, you should also explain now why is there electrical energy, because there's current, and the current, this is eddy current, by the way. If you really like the name and you want to put it in your explanation. So I will say EMF is induced. Eddy current will flow in the metal block, causing heating. This shows that the induced current is flowing in the metal block, the kinetic energy, and blah, blah, blah. All right. So bring it home. Talk about, in fact, you don't mention electrical energy also, never mind. But you have to talk about the last stage, which is heat, because heat is lost and you cannot get it back. So it's a heating effect, so-called heating effect. Okay, anyway, I hope the rest is learning also from the questions to write your answers a bit better. Next one. This one, I don't understand your question. What does it mean that field line almost parallel? Field line shows the direction of force. So if you are, hang on, I go and find a picture. So this is about the gravitational field line. On the, or close to the Earth's surface. So give me a sec to copy the image. Do I have a similar image here? Okay, this is good enough. Okay. So if I zoom into the surface, you can see they are almost parallel, right? If they're almost parallel, can I say that the line separation is the same? Can I say the line separation is the same? And the separation of field lines has something to do with field strength. Closer separation of field lines imply stronger field. Does that make sense? So for example, here the gravitational field is weaker. Here the gravitational field is stronger because you're closer to the surface compared to on the top ma. But if I zoom in enough, it will look like it's almost parallel. Hence, I can say that the field is same separation. Almost parallel is same separation. So same G field or same G. Okay. The direction of the field line shows you the direction of the force, but it doesn't show you the magnitude of the force. The magnitude of the force depends on how far apart the lines are. The further apart the lines, the weaker the field will be. Right? So let's see if this is a nice picture. Okay, this is a beautiful picture. Though not very clear. Let me see if I can get a clearer one. This, don't be scared. This is just a picture. If no, it's my picture. Yeah, never mind. I show you here. Okay. So this one, these lines, there are many lines here. Ignore the red color line, just focus on the blue color line. The red color line is another line, so ignore it. Look at the blue color line, okay? The blue color line shows you the gravitational field. Obviously, at this scale, nobody is uniform, lah, right? You are not close to the Earth's surface. Although, I guess, if I zoom in, like super zoom in here, and I don't think so much, it looks kind of parallel lah. If I just zoom in and I stand here, I need to zoom in some more, although my diagram cannot zoom in already. Okay, so if I stand here, it looks almost parallel. But let me zoom out again, and you want to stare at this diagram a bit. So if you look at this diagram, right, you see, at here, the lines are very close, so the field here is strong. As I move away from the Earth, the line become further and further apart. The field will be weaker, 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 weaker. You see this point P here? It's like there is no field line there. This is because the gravitational attraction between the moon and the Earth cancel out. So here is where the gravitational field is zero. That's why here there is no lines. All right. And then when I move closer to here, you will see that there are some lines here. There are some lines here. So actually, it's not just this point where gravitational field is zero. Gravitational field is also zero here, where my cursor is. It's also zero here. But we want to make your life easy and don't want you to do equilibrium or vector drawing. So we normally put them on the same line. So left equal to right. Okay, anyway. Yeah, so here, if let's say you look closer to the moon's surface, since moon's gravitational field is weaker, you can see the gap between the lines are weaker. All right. So if you draw a diagram, don't worry. No field line means no force. Got field lines means got force. Direction of arrow is direction of force. Gap between the line is the strength of the force or the magnitude of the force. So number 2, direction of arrow or direction of G is a direction of F. And then there is a damping question. This one is read the question law, because in this question, they already tell you, because your question is, how do I know that the amplitude is constant? Because the question tells you the amplitude is constant. Don't think too much, lah. The amplitude is constant. I know it won't be, and actually the more accurate one is to spiral inwards, but they say when the amplitude is this one. So while the oscillation may not express itself entirely in this blue color circle, but it will be on the blue color circle if the amplitude is 0.6. So don't overthink it. If they tell you it's 0.06, you just draw 0.06. I don't really understand this question that you are asking me. Total energy stored is the sum of the individual half CV square or CTVT. Why is energy CTVT lah? Wouldn't energy be also half total capacitance, total potential difference square? Was it the answer is yes, lah, it will be the same. If you have a way to calculate the total capacitance and the total voltage. And also this one a bit sus one because this total voltage, if like that, but the potential is different for whatever reason, then you cannot take the total voltage already. Because let's say this is 3 volt and this is 0 volt, voltage is not the same. What is the total voltage? Don't know. So this one kind of only works if your capacitor is like this, where your VT is the whole thing. You can try it out. Try it out with different equations. Because actually I don't know which question this is. I think it's this one. But I don't know whether I'm answering your question or not, because I don't really understand your question. You want to clarify? I think it's this one. Now, what do you mean by CTVT? This one is May, June 23P42. Okay. Maybe you tell me what you mean by CTVT in this question. Okay. So currently this one is V. This one will be charged to V. This is not connected. This is 0 volt. Is there energy stored? Got in this capacitor. This is C and this is 3C. Got energy stored. Only in C lah. So the energy here is half CV square. Do you want to use CTVT here? Do you want to be like, these two looks parallel? Although I can't really say it's parallel. So load B is not even here lah. So you don't want to CTVT here. Make sense? There will be no total capacitance because B is not connected to the power supply. Is that okay? For this one? No CT. B is not connected to the power supply. Okay or not? The first one. All right. Now we put it at Y. So this one connected. I guess my question to you is A and B parallel or series? The answer is neither. It is neither parallel nor series. Hence, there is no CTVT. Teacher, no parallel, man. No series, man. I don't know. Because there's no power supply. The power supply is disconnected already. If I look at the connection, it looks like parallel because the charge will flow until the potential is the same. And equal potential looks like a parallel thing. But then if I look at the charge flow, currently, this is all the negative charge, CV. This is all the positive charge. So then what will happen now is some of the negative charges will look at B and go like, ayo, you poor thing, you got no charge. Aya, I give you some lah, we share lah. So the electron will go this way. So if I look at current flow, macam looks like series. If I look at potential difference, because current or charge will flow until potential difference across A is equal to potential difference across B, then this one look like parallel. So I don't know whether it's series or parallel. Hence, I cannot cannot confidently sum up the capacitance. So I would rather just sum them separately. That is my response. So basically, I will flow from A to B until BA equal to BB. So this one would be C, BA is equal to 3C, BB. B is Q, Q is C. B is Q over C. QA over C. QB over C. I think I did this question in class already one. But basically, current will flow until the potential is different. This the same, sorry, equal. So when you see this, it feels like it's parallel. When you see the first one, it feels like it's series. I guess we can try. Was that not my method? It's basically what I did. C, 3C, and cut. So QA is 1/3 of QB. But QA plus QB is the original charge, which is CB. Let's continue do maths though. Okay. So in short, I don't know whether it's series or parallel. I don't want to sum them up because I don't think it's too much of a hassle to just add them together lah. But also, one of it will work one. One of it will work. I just don't know which one. Series or parallel, it will work. I just don't know which one. Feels like it's parallel. But the current flow look like it's series, so I prefer not to. Okay. Then I answered all your questions already. Let me know if I miss out anything. There's one final one, which is this. Your question is, does all the capacitor discharge at the same rate? The answer is no lah. No. Nope. No. I don't think they will ask you this lah, because it's too hard now for discharging. If they just ask you a normal circuit without the discharging equation, then possible. In fact, they only ask one time and then they realize they over asked already. So I don't think they will ask again now. You think Cambridge will set the question and then they'll realize based on the student answer that I don't think this is actually fair to ask the student. So they stop asking lor. Too bad lah on the student. But if you want to know, this is the question. May June 22 P42. This is series discharging. It looks something like this. But they can't give you a network of capacitor. It's too complicated already. Because you will need to derive a new discharge equation. You cannot use your V is V naught E negative T over R's. Of course, in this case, the R will be this R, and the C is actually your total capacitance because you have to discharge together. You cannot, because Q1 is equal to Q2. If you take away one charge from the 22, I must take away the same charge from the 47. Because they are series. Of course, then the question would be, what happens if I have parallel? Right? If let's say I have the same setting, basically I copy the same circuit, 12 volt here, and then still have my resistor here. My X and Y is still here. My S is here. But the only difference now is I have this in parallel. Right? If I have it in parallel, then when this one is connected, if the 22 wants to discharge, the 22 will discharge like that. Oops, so this is R. So for this 22 discharge cycle, V will be V naught E negative T over RC. Because of how it was charged in the first place, 12 volt, this is 12 volt. This C is your 22 microfarad. And this V is whatever V this is. They won't discharge at the same rate because there is also a second loop, meaning they are sort of like insulated from each other. I mean, provided the resistor don't burn now, okay? If the resistor stays consistent, then now this will be your second V, or this is V2. So this is V1. Then for the second one, will be V2 is equal to, V0 is still the same. This is still 12 negative T over RC. So this one would be 47 microfarad, but this is still 12 because when I put it at X and charge, everybody gets 12 volt. Your circuit where you drew resistor, parallel, series, I think a bit much lah. I think a bit much. In fact, this one also I think a bit much already. So I think it's a bit much. But if they really want to, you already know what to do. What? If they are in series, they discharge together. So the capacitance, the total capacitance. But this V has to be the total V here. VT. Then this one will be 12 volt. Okay. Whereas if they are parallel, their own independent little loop, provided the resistor doesn't burn because it's having double the current. Otherwise, if the resistor behavior is consistent, which it should be, then this is how you use the equation. So if they're side by side, which is the harder one, the capacitance, the total capacitance, the potential difference will be a total potential. You are treating these two as one thing. You combine them into one because they have to move together. It is just one loop. There's only one pathway. I cannot remove one electron from one without removing the other electron from the second one because of how it discharges. However, for this one, they are independent loops, so they can be treated separate. Yeah, who knows? Maybe you'll see this, although I think it's a bit much. Like that, then again, same thing. You loop by loop lah. Very much like your DC in AS. Loop 1, loop 2. Treat them separately. Okay. Any follow-up questions from the floor? Anything else you asked I haven't replied? This one is one. Okay. I think that's it. Okay, so with the time that we have, I will, I guess, very briefly run you through the nuclear physics. First, gonna go around 8. So for nuclear physics, there are two parts. Okay. The first part is binding energy. Okay, you know what? I'm just gonna yoink something from my previous self. Okay. I will share these notes with you later. Okay. So the first part is binding energy or mass defect equation, which is not unknown to you. Okay. It is basically the E equal to delta mc square. We have a delta here to show that it is a change in mass. All right. So when we use the equation, it's delta mc square. All right. So the important thing to understand is this is for a single nuclear reaction. Okay. Everything here is SI. And if the mass of the nuclei increases, that means energy is absorbed and is converted to mass. If the energy decreases, if the mass decreases, means that the mass is missing and is converted to energy released, converted from the loss in mass. Most of the time, obviously, in a nuclear reaction, energy is released because all nuclear reaction is due to something not stable. Nuclear bomb, if nuclear bomb need to absorb energy from surrounding, that's not a very useful bomb, right? The bomb should give out a lot of energy very quickly. So most of the time, your mass defect is a loss in mass. That's why we call it a defect, because energy is released. Okay. Now, when using this equation, immediately the first problem that we have is these units are too big for particles. We don't if we measure a particle in kilogram, there will be a lot of decimal points and a lot of problem. Just a point here. Okay. So we would want to find the energy equivalence of 1 UC square, meaning 1 U is 1 atomic mass unit. And I don't know whether you know or you remember from chemistry, 1 atomic mass unit is 1/12 the mass of carbon-12. We use carbon as the standard atom or the standard nucleus, but give it a mass of 12. So 1 U is 1/12 the mass of carbon-12. Carbon-12 atom. Okay. So you can find this in your data page. We'll put it into the UC square equation. And also, we will convert joule to eVolt. That allows us to press our calculator to arrive at 933.75 times 10 to the power of 6 eVolt, which can be written as 934 mega eVolt. You can use this if it's given it's based on the data in the question paper. If you use the calculator value, which is more accurate, you will get 931.5. Sometimes if they want to write in 2SF, they'll just write 930. So 1 UC square is equivalent to these numbers. Which number to use? Use the one that is given in the question. Very much like the speed of sound. Sometimes it's 340, sometimes it's 334, sometimes it's 333, sometimes it's 330. I don't even know. So follow the question. If the question didn't give you anything, then you have to do this conversion yourself. But this is kind of like a shortcut where instead of going through this painful pressing process, you can just use this now. They can also ask you to derive this for 2 to 3 marks, which is a bonus question. Just substitute. Remember to convert. Okay. So why is this important? Because we want to understand what is binding energy. Okay. So let's say once upon a time, the universe, the Big Bang Theory says that once upon a time, the universe was just nothing and then suddenly bang, all the particles come out, right? It starts off with quarks. You have quarks, and the quark will become proton and neutron. And proton and neutron will combine and form all the elements on your periodic table nucleus. This is where we are at right now. Okay. So if that is the case, somewhere, somehow, there was an energy used to bind the proton and neutron together to form the nucleus. Because by right, protons don't like to sit with other protons because they are positively charged. They should repel each other. But thanks to the strong nuclear force, they are tied together. Okay. So right now, if I want to study this strong force and I want to think about the stability of the nucleus, I will have this binding energy. But we want to define it in the reverse process. So if let's say some force or somebody did the work to put the nucleus together, then if I want to separate the nucleons, take out all the proton and neutron and throw it away to infinity, that will require energy. That will be my binding energy. Okay, so binding energy is basically how much energy we need to separate completely to infinity. Really just take the proton and throw far away, take the neutron and throw far away in the opposite direction. All the nucleons in the nucleus. So let's say you have a carbon 12. I tear apart the carbon 12 to 6 proton and 6 neutron and scatter them far away from each other such that they no longer attract or repel each other. So separate them completely. We can calculate this by just subtracting the difference in mass of the proton and the neutron. So we sum up the difference in mass of the nucleons minus the initial mass of carbon. So you minus one. And then I realized that it is positive, meaning the mass of these 12 things is slightly more than the mass of carbon 12 itself. Which it also tells me that because this mass of carbon 12 is smaller, carbon 12 is more stable. It has less energy. And because now I split this, energy is needed. Makes sense, right? If I want to tear the carbon apart, I need energy lah. Why would the carbon just disintegrate? It would be very scary there because we are made out of carbon. We are made out of three things: carbon, hydrogen, oxygen, and other stuff. But we are mainly still carbon, hydrogen, oxygen, CHO, organic chemistry, question mark. So if the carbon in our body can randomly just become proton and neutron, that means one day you just suddenly just not there anymore. Like you just become proton and neutron. So thankfully that doesn't happen. But we can isolate out the carbon and split it apart. We want to know how much energy it needs because based on this, we can calculate how stable the nucleus is. So if I want to find the binding energy, I will then take the difference in mass. This is in terms of U and throw it into the MC square equation. But because there's a UC square here, this UC square can be substituted straight away as 934 mega eVolt, which is our preferred unit. Of course, if they never give you 934, then you slowly lie low. U is 166, 10 to the power -27. C square will be 3 times 10 to the power 8 square. The unit here will be SI in blue, but most of the time for atoms, we prefer the unit in mega eVolt. Okay? So this is binding energy, meaning the total energy I need to separate out the 6 protons and 6 neutrons. But you would then say, then teacher, the bigger the nucleus, the more energy I would need, right? Because I have more neutrons and I have more protons. You are right. So for a more accurate measurement about how much energy I need and how stable the nucleus is, I would divide by the nucleon number. That's why per nucleon number. Yes, and the larger this number is, the more stable the nucleus. If you plot a graph of binding energy per nucleon number, we'll get roughly this shape. Okay, and the peak here is hashtag goals, the most stable. This is iron. I think this is 8 point something mega evo. Okay. So if let's say a nucleus finds itself too far away or its binding energy per nucleon number is too low and it is not stable, it will fission or split apart if it's too big. So it's a nuclear fission, it's a splitting of a large nucleus into two smaller, more stable nuclei. But if the nucleus find themselves too tiny, like for example, deuterium, tritium, this one normally happens in the sun, they will combine and fuse together. The closer they can get to iron 56, the more stable they are. And if you study chemistry, you will understand that there's this universal concept. Anything that happens in nature tends towards a more stable form. Everything wants to be a bit more stable, including you, right? So tends to be a bit more stable. So too big, split apart. Too small, combine. Why is this here? Okay, anyway, I shall ignore that. So when you calculate binding energy, right, when they give you the equation, okay, you want to calculate the binding energy, you would also want to understand that sometimes they will give you the binding energy. Sometimes they will give you mass defect, and sometimes they will give you the mass on its own. For example, in this question in May, June 23, the question here gives us the mass defect. Okay, so for you to understand what mass defect is, this is basically deuterium or hydrogen, where it consists of one proton and one neutron. This one consists of one proton and two neutrons. This is helium-42, two proton and two neutron. So this mass defect is actually the mass of the proton plus the mass of the neutron minus the mass of deuterium. Because to do the mass defect equation is 21H becoming one proton plus one neutron. This is 31H, separate completely to infinity, one proton plus two neutron. This is 42 helium, separate completely to infinity, two proton plus two neutron. So whatever number you have here is actually, they already did the mathematics and they already calculate and they just give you the final sum or the subtraction. Okay. Which means now, if let's say you see a nuclear fusion process like this one, and they ask you to name, now just keep me kicking. They ask you to name the particle X or balance the equation. This should be the amount that you use. For the mass of nucleus, can we use the rest mass of proton? Okay, so for the masses, you generally do not want to use the data table. If you look at the past year questions, let me close some windows first. If you look at the past year questions, they will give you data, you should use their data. You don't go and use your own data, okay? So for example, they will give you the mass of the neutron here and the proton here, you use whatever they give you. Okay? Use the number given in the question. This one is binding energy. Nope, this number. Like this one. Notice that they all give different SF one. Like 2019, they give like 4 SF, but then just now the question that I pointed out to you, this one, they give 6 SF. Okay. You get my point? Please use the data in the question. Don't use the data in front. This one, I don't even know how many SF, man. 1, 2, 3, 4, 5, 6. It's a telephone number at this point. 9 significant figure. So you don't go and take 204 multiply by 166 times 10 to the power negative 27. No, 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 no. Use the data given in the question. Don't use 204, use this one. But you still need to use U. So the only data you can extract from the table is this and this and this. Okay, mass of proton, mass of neutron. Please use whatever the question gives you, if the question wants to give you that mass. Like for this one, the question did not give you the mass of proton and mass of neutron. You are not supposed to use the mass of proton and mass of neutron. You are supposed to use the binding energy. Okay, so binding energy release is actually the difference in binding energy of the product minus the reactant. So in this case, the binding energy of the product only got helium. And this is the delta M of the product. Okay, so just for you to understand what is going on here, this is my reaction. I have deuterium and tritium combining to form helium-42 and neutron. Number one, proton, neutron, electron got no binding energy because it is not a nucleus. It's just a free agent, no binding energy. The only thing that has binding energy is deuterium, tritium, and helium, these three things. So the product is this. Okay. And this 0.30377 is the mass defect of helium. But this is not the binding energy. To find the binding energy, I will take the mass defect times C square. So it's 0.03070 0.03037 UC square. Okay, so it's 0.03037 UC square. But I factorize the UC square. So this is the product. This is helium minus the reactant, which is your tritium and your deuterium. I think 228. This is your deuterium. This is your tritium. 21H, 31H. UC square. Did they give me 934? Nope. So I will have to, or rather I don't need to because it's in June. So I'll put this out this way. Another way people can do it is obviously to calculate it separately lah. You delta MC square for 21H, then delta MC square for 31H, you add them together, and then after that you bring back and subtract. But I don't see a problem of putting them together. Okay. So in other words, what's going on here is we will need to subtract or think about energy release as the difference in binding energy. So we'll take the binding energy of the product minus or subtract the binding energy of the reactant. So this is not a familiar way to use your delta MC square. Because previously, whenever you use your delta MC square, you write a balance equation, and then you use the mass of the nucleus minus whatever you have. You look at the mass of the reactant minus the mass of the product. But the mass of the reactant and the mass of the product can be substituted with the binding energy of the product minus the binding energy of the reactant. Because, let me highlight here first. You want to find energy, you will take the mass of the product minus the mass of the reactant, and then UC square or delta M C square. This whole thing is delta M. Product minus reactant. But if you don't have the mass of the product, in this question you don't have. You only have the mass defect. So it can also be the mass defect of product minus the mass defect of reactant, C square. It can also be the binding energy. Mass defect of product minus mass defect of reactant C square. If there's a U, then you have to convert the U away lah. All right. It can also be the binding energy of product minus the binding energy of reactant. Okay. So this one is pretty important because sometimes they will give you different data. Like for example, this one, you are given the mass defect. So I take the mass defect of the product minus the mass defect of the reactant. If you want to know why I can use the mass defect, because students are curious, I have included the derivation here. I've written the mass defect, right? And for each of them, I got the binding energy equation. And then I just do simultaneous equation, which I've outlined here, so that I finally arrive at the balance equation. And if I'm doing this to the equation, I will also do this to the binding energy. Binding energy 1 plus binding energy 2 minus binding energy 3. So you can go and check out the derivation here. I'll send you the recording of this class also, okay? But the whole point here is you have to understand that at the end of the day, the binding energy is one way to find the energy release. You find the difference in binding energy. Another way is to find the difference in mass defect. And the other way is to just find the difference in mass. All three will work. Difference in mass defect, difference in binding energy. Hey, this one only C square, sorry. All three will work. Depends on the data that is given to you. So you should go and at least practice some questions. Here are some suggested questions. Some of them are more direct. They directly give you the mass of the nucleus. That way your life is easy. For example, like this one, they give you the mass of everything. They give the mass of helium, the mass of plumbum, the mass of polonium, and you just need to minus. Okay, but sometimes they will give you, instead of the mass, they will give you everything. Mass, total mass, mass defect, binding energy per nucleon. This question, if you understand this, then you will understand how to use different data. Teacher, do I need to use all the data? No, no, no. You don't need to. In fact, this data, this 95765, subtract now 94906 is this one. Mass of the nucleus, total mass of the separate nucleons. When you subtract these two, you will get this. So you can try out the questions. The other ones are like this one. They'll give you the mass of the product of all the separate constituents. This one you can subtract as usual. But then if you look at the more recent questions, they have started giving students binding energy as well. The question I was discussing just now is this one. They give you the mass defect. Then I think there are also other more recent ones that they give you the binding energy straight away. So in short, just a heads up, energy release can be the difference in binding energy. Energy release can also be equal to the mass of the product minus the mass of the reactant, C square. Energy released can also be mass defects. So you need to add the mass defect of the product minus the mass defect of the reactant, C squared. Okay, so I'll send you a recording of this class just so that you can start doing your stuff. See, this one, they give you binding energy. And if you have any follow-up questions, you can ask me. But I think on Friday, I will talk about the decay law. All right. This one was recorded from another class. But today, I think I spent some question clarifying all your magnetic fields problems. So hopefully that was helpful. And Friday, let me think. Friday, I really would like to finish the syllabus. Okay, so if there's any questions, I will not answer them on Friday at all. I will answer them in our last class. Okay, yeah. So go try the mass defect question. I will send you a link to this recording. You may need to fast forward a bit because I'm pretty sure I discussed something else with these people as well. But it's a different class. I will share it with you. Okay, as a stand-in because we are a bit lacking of time today. All right, take care. I'll see you. Do the easy one first. We will do decay law next round. Bye.